Okay, in this video I'm going to continue on my tutorial videos on thermodynamics and statistical mechanics. We're on video number 4 and this is going to be on the ideal gas law. It's going to be a bit back to front. I probably should have done this earlier, but I'm doing it in this order, so be it. The previous video, which to be honest has nothing to do with this, but it is the previous video nonetheless, I spoke about compression work and I went from work as a function of volume for compression is P dV or NKT, the natural logarithm of VI over VF. So the ideal gas law. Well, the ideal gas law came from a number of experiments that were performed. You had Boyle's law, you had Charles's law, and all these. I'm not really going to talk about those because, to be honest, I don't think we really need to. What's important is the ideal gas law is empirical. In that it wasn't derived from anything really. I suppose it's just an experiment. These are experimental facts, and they're summarized quite well in what's called the ideal gas law. So let's write it down. The ideal gas law says that PV is equal to N or T. So let's start and look at the different parameters. So of course we have pressure, we have volume, we have temperature. Now what are these two here? What is N and what is R? Well, the answer is as follows. If you're a chemist, you'll know that small n is the number of moles. Okay? And a mole of molecules is Avogadro's number of molecules. So if you have 1 mole of a substance, N sub A like this is Avogadro's number. Just a constant, it's Avogadro's number, and it's 6 times 10 to the 23 molecules. So if you have a series of molecules or a packet of them, and you have 6 times 10 to the 23 of them, you have what's called 1 mole. So we like to talk about the number of moles, especially if you're a chemist. So small n is the number of moles. So let's say, for example, you had 3 times 10 to the 23 molecules, you would have 3 moles. And R then is, I'm going to call it the molar gas constant. Molar gas constant. Okay, and it has an empirical value. So R is equal to 8.31 joules per mole per Kelvin. Now what's important here is temperature is measured in Kelvin. They're all in SI. Pressure is measured in pascals. Volume is measured in meters cubed. Okay, and N, of course, N is just a constant. Alright, so what else can we say about this? So we have the molar, it's just a constant. So we don't need to worry about R. But there is something interesting here. We know that 6 times 10 to the 23 molecules is equal to 1 mole, or is N. N is the number of molecules. So, N is the number of moles. So capital N is the total number of molecules, is of course going to be small n, the number of moles, times Avogadro's number. Alright, so let's just arrange this because we know that PV is equal to nRT. So let's see if we can somehow sub in for this n here. If we do that, we find that n, small n, the number of moles, is the number of molecules divided by Avogadro's number, and that means that pressure times volume is equal to the number of molecules divided by Avogadro's number times R times T. Okay? So I'm going to write this in a new way. PV is equal to N times R over NA times T. Now, great. And I'm going to tell you that we actually call, although this is a constant, we call it something else. We give it a placeholder K, and I'm sure you know what I'm talking about. We're talking about Boltzmann's constant. This is Boltzmann's constant. It has a value of 1.38 times 10 to the minus 23 joules per Kelvin. Alright, so if you write it this way, we have a new ideal gas law? Well, I say new, it's just a new way of writing the ideal gas law. So we can have PV is equal to small n times the molar gas constant times temperature, or PV is equal to capital N, number of molecules, times Boltzmann constant times T. So now hopefully you can see why I call this the molar constant and I call this the molecular constant. Okay, so if you're wondering which one do I use, when do I use, with which of the n's do I use K and with which of the n's do I use R? You know that with the molecular gas constant you use the number of moles, and with the with the molar gas constant you use the number of moles, and the molecular gas constant you use the number of molecules. Pretty straightforward stuff. So we can summarize, or we can summarize the relationship between the molecular and molar gas constant by saying that we had R is equal to Avogadro's number times K. I like to think about it, R is equal to Na times K. That's just the way I remember it in my own head. Now the ideal gas law is quite good. I'm going to write it as capital NKT. The molecular gas, or the ideal gas law is great because for many years it predicted loads of things for us. So units aside, the ideal gas law summarizes a number of important physical facts. So we see that for a given amount of gas at a given temperature, doubling the pressure squeezes the gas into exactly half as much space. So if we look, this side equals this side. So if we double the pressure, we must halve the volume. That's one of the properties of the ideal gas law, because we haven't changed the temperature and these here are constants. So the only thing that can change is the volume. Alright? Or at a given volume, doubling the temperature causes the pressure to double. So if we hold the volume fixed, so PV NKT, if we hold the volume fixed, that means these three here are fixed. So if we double the temperature, that means we must double the pressure. Alright? So just actually, I think this is a better way of looking at it. If we have PV is equal to NKT, if we are holding the temperature fixed, that means this side here is all constant. So if we double the pressure, we must have the volume. If we double the volume, we must have the pressure. Okay, in order for the equation to hold. So for nearly all the laws in physics, the ideal gas law is an approximation, or like all the laws, it is an approximation, and it's never exactly true for a real gas in the real world. However, it is valid in certain circumstances, and this is important. So when is the ideal gas law valid? In the low density limit. So when your gas is of low density, then it is valid. So if somebody asks you a problem and there's large density, well then the ideal gas law will just break down. And you'll find that, we'll say at room temperature and atmospheric pressure, the average distance between molecules in the air is roughly 10 times the size of a molecule. So the ideal gas law is accurate enough for most purposes. However, if you're talking pretty advanced physics, or even chemistry, you're often going to be talking about high densities. And if you're talking about high densities like plasmas and so on, the ideal gas law absolutely will not hold, and you must come up with something else. Okay, so that's all I've got to say about that. Thanks for watching. Please pass it on to your friends, subscribe to my channel, and if you're in a good mood, you might also click on an ad. Thank you.